Okay, here's our first launch for 2.1, and this is a problem I put together years ago. Another true story. While in Central Oregon, rafting to the Deschutes River, my raft scraped a sharp rock while going through Oak Springs. At full capacity, the raft is filled to an air pressure of 80 pounds per square inch, and my air pressure is declining at a rate of 1/10 of a pound per second. Model this situation algebraically, and let's hope I have enough air to make it to the takeout where we will portage the falls. Okay, so let's set up our sequence. How much air does the raft hold? What's the air pressure? 80 pounds per square inch. So let's start with an 80 right here. Okay, and that'd be probably in this instance my zero term. All right, and then the air pressure is declining at a rate of 1/10 of a pound every second. So in 1 second there'd be 79.9, 79.8, 79.7, and 79.6. It looks like we're probably going to have to, with these numbers, do a broken y-axis when we graph. We might even change our x scale on our table a little bit. And like we said earlier, this 80 will be at 0 seconds. So second 0 right there. Okay, let's break out our modeling data frame and put this together. All right, so no diagram necessary. And we said we'd start with our first x, a 0. And let's see now. Let's think about this. I want to see these numbers dropping significantly. All right, so let's scale. Why don't we scale by about, I don't know. Think about that a second. Well, if I'm dropping 1/10 of a pound per second, then in 10 seconds I drop a pound. That'd make this kind of clean right here. So why don't we go by tens? Yeah. All right, and these are all my x's right here. And now my f of x's, my outputs. All right, well, we started with 80 pounds. Okay, and in 10 seconds we will drop 1 pound to 79, 78, 77, 76. That cleaned up real nice right here. All right, now how are we going to scale the x-axis to make this happen? Well, let's see. Oh, yeah. First, let's talk. I can't look at the table right here for my common difference because my x interval is not 1. So I have to go back to my sequence. And you see that we're subtracting 1/10 every time. So we have a common difference of negative 1/10. Negative 1/10. All right. Now let's go to our scale. All right. So I'm going to make every hash mark 5. So I'm going to go 10, 20, 30, 40, 50, 60, 70, 80, 90. Oh, that's nice. 100 right there. All right. And now when I look at these f of x values, my outputs, we're talking 80 to 76. So I am going to break my y-axis. Big values there. And let's just start at a number a little bit lower than 76. Let's see what I did. Yeah, 73. And then let's go, I probably went up by, well, I've got to get up to 80 there, right? So did I go 74 right here? I did. 75. 76. 77. 78. 79. And 80. All right, let's plot some points now. And because of my x scale over here, I'm just going to plot each point individually. So I'm going to go when x equals 0, f of 0 is 80. And then when x is 10, f of 10 is 79. When x is 20, f of 20 is 78. Now this pattern is just going to continue, but let's just continue to look here. So when x is 30, f of 30 is 77. Right there. And when x is 40, f of 40 is 76. Right there. Now, I can go a little bit farther, but I don't want to get beyond the broken y-axis, so I don't want to go below this right here. So let's just go, keep the pattern. 2 hash marks down, 2 hash marks to the right there. 2 hash marks down, 2 hash marks to the right there. And let's see, did I go one more? I might have. 2 hash marks down, 2 hash marks to the right there. And again, that's as far as I would go because my y-axis or my vertical axis here is broken. I don't want to go down into this region right here. Okay, so now let's talk a little bit about what this graph is telling us. Common difference, all right? So that tells me all kinds of things about the sequence and the function. So the sequence is, well, if I have a common difference, isn't the sequence arithmetic? And if I have an arithmetic sequence, isn't the function going to be linear? That looks like a straight line to me. Oh yeah, there we go. And the data shows a pattern of then linear. Now though, what is this, linear growth or linear decay? My slope is negative, so that's going to give me linear decay. Now let's go to our explicit formula. Well, we've got our first x is 0 and a linear function, so can we just go back to slope intercept? Just a second, Roxy. Let me finish up this recording right here. So f of x equals, general form of slope intercept would be mx plus b. Alright, so f of x equals, and slope is the same thing as our common difference, negative 1/10. X plus b, my y-intercept is the 80. So negative 1/10 x plus 80 right there. Good. And now finally our recursive formula. All right, f of what is what? This is function notation for our very first ordered pair in the table. So f of 0 is 80. And then our recursion equation, f of x is f of x minus 1, my previous term. And what do we do to the previous term every time to get the next term? Well, we subtracted 1/10. Minus, and I wrote that as a decimal, 0.1 minus 1/10. You could go decimal or fraction right there. And that's the model of the rafting problem. Thank you very much. Okay, lunch number 2. Same situation, rafting in Central Oregon on the Deschutes River. Okay, so after collecting more data on yesterday's rafting situation, because every time we go rafting, what do? We collect data. I'm joking. All right, I discovered that as I lose more air pressure, the rate at which I lose the air decreases. Good thing, as Shears Falls is right around the bend and I need my air to last a little longer. I want my air to last so I can get down to the takeout right before the falls. Anyway, it turns out that every minute I'm losing 5% of my air pressure. Model this situation algebraically if my raft was at 80 pounds per square inch when it was full. All right, so let's set up our sequence. And what did my raft start at when it was full and did not have that leak? 80 pounds per square inch. That's an 80. And now, what is my pattern of change here? Well, I'm losing 5% of my air, every minute. So if I'm losing 5%, and whenever you see percent, you think you're going to have a common ratio, all right? And if I am losing 5%, doesn't that mean I will still have 95% left? So my common ratio is 95% as a decimal, 0.95. So now let's just punch out some numbers. Let's go 80 times 0.95, and that will give me in 1 minute 76 pounds per square inch. And then if I take that and I multiply it by 0.95, I'm going to get 72.2 pounds per square inch. And if I multiply that by 0.95, I'm going to get 68.59 pounds per square inch. And if I multiply that by 0.95, I'm going to get 65.1605 pounds per square inch. Now, If you had rounded these decimals, that's appropriate. Try to be consistent when you do. That last number, I got to the 0.1605, so I just did each of these exact. All right, and then I've got to think, this 80, is my first x going to be a 0 or a 1? Well, that's the pounds per square inch that my raft had when it didn't have a leak, so I'm going to probably call that minute 0 right there. Minute 0. Okay, so let's go to our modeling data frame, and there's the sequence right there. We don't need a diagram, although I should have a pretty picture of Shears Falls. You know what I'm going to do? I'm going to get a picture of Shears Falls next time I do this one. Okay, next, x's. Well, let's think about this. We're going to start with an x of 0, minute 0 right there. Okay, and I think I could just go minute 1, 2, 3, 4. That looks pretty good. 1, 2, 3, and 4. And then I think to myself, okay, my f of x values, well, let's put an x down here at the bottom. And so on, x. Okay, now what is f of 0? 80. What is f of 1? 76. What is f of 2? 72.2. What is f of 3? 68.59. And what is f of 4? 65.1605. Beautiful. All right. Now, think about this. I multiplied by 0.95 every time. So that's a common ratio, isn't it? So common ratio of 0.95, that's my pattern of change. I'm multiplying by 0.95. And I'm trying to get you guys to the point where you can fill in all of this right now, before you look at the picture. So if I have a common ratio, that means this sequence is a geometric sequence. So geometric. And if I have a geometric sequence, that means the function that we're going to create is going to be exponential. That means the data, when we graph it, is going to show a pattern of exponential. And then I look, my common ratio is between 0 and 1. So that's going to be exponential decay. If this common ratio is bigger than 1, I will have exponential growth. Look at that, without even looking at it. Now, let's plot our data and make sure our data shows this. By the way, I don't have a lot of data, so it may be challenging to see the concavity of my exponential curve, but even with a little bit of data, we should show it slightly. So let's find out. So let's scale the x-axis like we normally do. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And look at my lower f of x is 65.1605, and then it only goes to 80. So this might be a really good opportunity to break the y-axis. Let's see if I did that. Yes, I did. So I'm going to skip a bunch of y values here and probably start with a number 65 or maybe a little lower. Let's see. How about 60? All right. And now if I go by 2's, can I get up to 80? I bet you I did this. 61. See if this is 62. Oh, I'm going by 2's. So 60, 62, 64. That means 66, 68, 70, 72, 74, 76, 78, 80, 82, 84, 86, 88, and that worked great. I definitely have my 80 there. So let's go ahead and plot this 0, 80. When x equals 0, f of 0 is what? 80. And when x equals 1, f of 1 is what? 76. Nice. Right there, 76. And when x is 2, f of 2 is 72.2. So right about that 72. I mean, slightly above it, but that's going to be hard to show. Okay, I exaggerated that a little bit, you guys. Okay, and then when x is 3, f of 3 is 68.59. So there's my 68. So this would be 70, so 0.59 would be right in here. Not bad, okay. And then when x is 4, f of 4 is 65.1605. Well, let's get this absolutely perfect. I'm joking, that's hard to do, but we'll do our best. 64, 66, 65 is going to be right in there. And there's my data. It'd be hard to continue, so I'm going to leave it just like that right now. Okay? Now, remember what I said earlier? I know this has to be exponential, but because of my limited amount of data right here, it almost looks linear. But if you look very carefully, it is slightly turning, and it's going to turn more and more as I go farther and farther and farther. So there's my exponential, slight concavity right there. And it is slight because our common ratio is 0.95%, or I should say 95%. And it's decay because my outputs are getting lower and lower and lower. So exponential decay. Now, let's go to our explicit formula. Exponential function with an initial x of 0, our general formula will be f of x equals a times b, and because of that x equals 0, I'm going to go to the x power right there. So f of x equals, now know your parts, a is your initial output, 80. B is your base, or your common ratio, 0.95 to the x. So let's put this expression down here in our table. Beautiful. And now the recursive formula. Oh yeah, there's the function right there too. Oh, that's pretty. All right. So remember, game show, what's behind door number 1? My first x value, 0. What's behind door number 2? My first output, 80. There's my initial term in function notation, f of 0 equals 80. And then my recursion equation, f of x equals f of what always goes behind door number 3 to represent a previous output, f of x minus 1. And what did we do to the previous output every time to get the next output? We multiplied by the common ratio, 0.95. So let's just go times 0.95. There it is. All right, so here's our activity for 2.1, connecting the dots, piggies, and pools. And this is a develop understanding task. So today I'm going to introduce a discrete function versus a continuous function. And we'll start talking about a little domain. All right, this is just an introduction of that stuff, and we'll develop it throughout this module. So, number 1. My little sister Savannah is 3 years old. She has a piggy bank that she wants to fill. She started with 5 pennies, and each day when I come home from school, she is excited when I give her 3 pennies that are left over from my lunch money. Use a table, a graph, and an equation to create a mathematical model for the number of pennies in the piggy bank on day n. And we're even going to do a few more models than that. All right, so let's start with a sequence. Okay, and you think to yourself, how many pennies did Savannah start with? Well, she had 5 pennies, so our first number in the sequence will be 5. All right, then on each day when I come home from school, she is excited when I give her 3 pennies. So that means, what am I going to do? I'm going to be adding every time, and that's a common difference. So this is going to be an arithmetic sequence with a common difference of, and I'm adding how many pennies? 3. So that's going to make this an 8, 11, 14, 17, and so on. Now we have to make a very important decision. Are we going to call this the 0 term or the first term? And we have to base that upon the context of the problem. So she started with 5 pennies. With that statement right there, I'm going to call this day 0. So that makes that 5 a 0 term. And then first, second, third, and fourth term, and so on. Okay, let's finish the rest of our models then. We don't need a diagram. So let's go to our table where we are starting with an x equals 0. And it makes sense then to go day 1, day 2, day 3, day 4. So let's go 1, 2, 3, 4. Those are all x's right there. All right. And now my corresponding f of x's, so f of 0 would be 5. F of 1 would be 8. F of 2 would be 11. F of 3 would be 14. And f of 4 would be 17. All right. So let's talk about our pattern of change and start setting up our graph. So we said we had a common difference in the sequence, and the sequence has a common difference of 3. We are adding 3 every time, so d equals 3. And now we're going to work on filling this stuff out even before we have the visual graph. All right. With a common difference, we know that the sequence is arithmetic, and an arithmetic sequence leads to a function that is linear. So when I graph it, I should have a straight line, and that means the data shows a pattern of linear. And now we don't even need to look at a graph to answer this. Is this linear growth or linear decay? Well, I'm adding every time. I have a common difference of 3, so that means we're going to have linear growth. Okay, so let's set up this picture and make sure all of this is happening. Okay, so x is 1, 2, 3, 4, so let's just do our typical 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Now, my f of x's are to 17 already, so I'm probably going to want to go by 2s. Let's see what I did here. What if I go 2 right there? That'll get me to 19. I might just go by 1s here. 1, 2, yeah. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, that's fine because I have a 17 right there. Okay, so now let's plot our points. When x is 0, f of 0 is 5, so 0 and up to 5 right there. And now we could probably do slope pretty easily right here. The common difference is 3, that means I have a slope of 3. So I'm going to rise 3 and run 1. Well, let's go up 1, 2, 3, and then go over 1, but that's just 1/2 there, so I'm going to go right to there. And I could keep doing that pattern. Now it's probably easier with my different scale down here if I just link hash marks. 3 hash marks, 2 hash marks. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. And let's do that. Do I have room? I don't have room. I'd be off the graph. Okay, so that's all I'll plot right there. All right, and look at that. Does that look linear? Yes, it does. That's a perfect straight line. And are we growing? We certainly are. The data shows a pattern of linear growth. Look at that. We knew that because of the common difference of 3 before we graphed. Now, explicit formula. Well, a linear formula, okay, with my first x0, that's just your old slope-intercept. F of x equals mx plus b. So that implies f of x equals, and my slope m is my common difference. I'm going to write that as a 3, or I could go 3 over 1, plus my b is my y-intercept. I see it right there as a 5, or in my table 0, 5, plus 5. So down here, let's write the expression 3x plus 5. That's every f of x right here. Now our recursive formula, f of x equals 3x plus 5. What a pretty graph. All right, let's play our game. F of blank equals blank. Well, what's my first x? It's a 0. So f of 0 equals, and f of 0 is the 5. And then f of x equals f of x minus 1. And then what's our pattern of change? It's a common difference. So every time we are adding 3 to the previous term. So let's just go plus 3. And there's the perfect model to that problem right there. Okay, so here's number 2. Our family has a small pool for relaxing in the summer that holds 1,500 gallons of water. I decided to fill the pool for the summer. When I had 5 gallons of water in the pool, I decided that I didn't want to stand outside and watch the pool fill. This is going to take a little bit of time. So I had to figure out how long it would take so I could leave, but come back to turn off the water at the right time. I checked the flow on the hose and found that it was filling at the pool at a rate of 2 gallons every minute. Ooh, 1,500 gallons, that's going to take a lot of time. Use a table, a graph, and an equation, and we'll do all our models, to create a mathematical model for the number of gallons of water in the pool at t minutes. And we'll go ahead and use x's instead of t's here, but you could use t's if you want. Okay, so now, let's see. When I had 5 gallons of water in the pool, so that means my first number in my sequence, which is going to be our first model, would be a 5. I decided that I didn't want to stand outside and watch the pool fill, so I had to figure out how long it would take so that I could leave, but come back to turn off the water at the right time. I checked the flow on the hose and found that it was filling the pool at a rate of 2 gallons every minute. So that means I'm going to have a common difference because I'm adding. And how much am I adding every minute? 2. So I have a common difference of 2 between terms. So that means 5 plus 2 would give me a 7, a 9, 11, 13, and so on. So there is my sequence right there. This is one of our models. Now, are we going to call our first term in the sequence the 0 term or the first term? Now, let's think. When I had 5 gallons of water in the pool, so this is really my starting point. So I think I'm going to call that the 0 minute, minute 0 right there. Okay, good. Now, this is for domain, which is going to be a new concept introduced today. How long is it going to take us to fill this pool? Okay, so let's figure out how long that's going to take. Let's just set up a little fraction here for division. All right, now I had 1,500 gallons, or that's what my pool holds. But I've already put 5 gallons in the pool. That means we have 1,495 gallons to go. And I get 2 gallons every minute. So if I divide that by 2, I'm going to know how many minutes this is going to take. So what is 1,495 divided by 2? That's going to be 747.5 minutes. That's going to take quite some time right there. So this is why we didn't want to stand and watch it fill. All right, that's great. So we have a sequence. We have all the information we need right here. Let's do the rest of our models. Here's my sequence right here. And now we go to the table, and remember, we're calling that 5 the 0 term. So let's start with an x equals 0. Remember, diagram won't be necessary here. 0. And then let's just go every minute here. 1, 2, 3, 4, and so on. And every one of those minutes, they wanted us to use a t, but we're going to go ahead and use x. Okay. Again, you can use a t if you want. Call that t, call that f of t. Now, let's find our outputs f of x. So f of 0 will be the 5. F of 1 will be the 7. F of 2 will be the 9. F of 3 will be the 11. F of 4 will be the 13, and so on. And we'll do our expression when we get our explicit formula in a minute. Some of you might be ready to make that jump right now. Okay, so let's talk about our pattern of change here. Look at the sequence. Common difference. Common difference of what? Well, what are we adding every time? 2. So d equals 2. What does that imply? Now, I'm hoping you guys can fill in these blanks right now. So the sequence is blank. Well, if I have a sequence with a common difference, Isn't that going to be an arithmetic sequence? Number 2, the function is blank. Well, if my sequence is arithmetic, then my function will have to be linear. So when I graph it, I'll see a pattern that's a straight line. It's actually going to be growing too. But that's number 3. The data shows a pattern of, well, we know it's linear, and because our common difference is positive, we're adding a positive number every time. That's going to be linear growth. Now, let's go ahead and set up our graph to show that. All right, let's put our x's as in 0, and then we'll go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Now, again, it's going to take, what, 747.5 minutes to fill this pool, and we only went up to, what, the 10-minute mark. So this is not a good diagram to show the entire situation, but it is linear, so the same pattern would continue, so it will work for us. All right, now we need to get up to at least 13, so I could probably go by 1/2 1, or maybe I went a little farther. Let's see. I think I probably went 1/2 1. No, I went 1 2. Okay, 3 4, 5 6, 7 8, 9 10, 11 12, 13 14, 15 16, 17 18, 19 20. So I see I went by ones there to get to 18 up top because I need at least 13 there. Okay, let's plot our points now. When x equals 0, f of 0 is 5. So x is 0 and f of 0 is 5 right there. And then we're going to go 1 7, so x is 1 and f of 1 is 7 right there. Now, I know this is linear, so this pattern is going to continue. Now, I have a slope of 2, all right, so I'm rising 2 and I'm running 1. Remember, horizontally, we're going by 1/2. So let's just use that. You could go right from your points again, too, but I think this is more efficient. There's a point, 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 and we have room for one more, a point right there. Note, linear, that's straight line right there. It's linear. And also notice I did something a little bit differently here. We usually do a dashed line, but this is a solid line. I wonder why I put a solid, and it's really not a line, it's a ray, because I'm starting here and I'm going through all of these points, and then I have an arrow at the end, meaning I'm going farther and farther and farther. Why solid? Well, let's save that thought for just a moment. Let's do now what we normally do, our explicit formula. So f of x equals, well, a linear equation with your first x0. Isn't that your old f of x equals mx plus b? Let's fill in the blanks. F of x equals, and m is my slope. My slope is the same as my common difference, 2, meaning what? I'm rising 1 2 and I'm running 1/2 1 every time. Okay, and then plus b. B is my y-intercept. That's a 5. So let's go ahead and put this expression 2x plus 5 into our table down here at the bottom. Makes for a beautiful table. Now our recursive formula. Oh, let me put the function on my graph. And now our recursive formula. So f of what number is what number? This is your initial term in function notation, which is just function notation of this first point right here. So when x equals 0, put a 0 right there. F of 0 is, and f of 0 is 5. And then f of x equals f of x minus 1, our previous term. And what do we do to the previous term every time? Looks like we're adding 2, and that is our common difference, 2. So let's add 2. And there's the models for fill in the pool. Now, this is some bonus coverage right here. I want to introduce where we're going to be going. Okay? So, remember when we talked about this line being solid? Why solid? Well, we're going to have two types of functions. We're going to have what we call discrete functions and then continuous functions. Now, a discrete function is typically where my inputs and outputs are whole numbers. And with a discrete function, the graph is only the scatter plot. It is, where's my arrow? There it is. It's just the dots. So if we want to put a line through our dots to kind of see the pattern of change, the visual, we always do a dash line. That means the line itself is not part of the graph. But this is a continuous function because we're talking flowing water. The water is flowing into our pool continuously. So it makes for a continuous function. So f is a continuous function. So in this module, we're going to work on the difference between continuous and discrete with a domain of x equals. Now, if I have a continuous function, I'm talking about all of the x values in this graph, like 0, 1, 2, 3, 4, and so on, except, all right, continuous means we have x's in between the zeros and the ones. We have fractions, we have decimals. It's continuous. Time is continuous. So I'm going to say f is a continuous function with a domain of x equals, and now we're going to use what's called interval notation right here. So interval notation means I'm going to either use parentheses or brackets right now. And I'm going to start you with brackets. All right. And then what is the first x value in this problem? It is a 0. So my first x is 0. I'm going to start at 0, my 0 minute, okay, right there. And then remember on the previous slide when we asked, how long is it going to take to fill the pool? Well, let's go back there. It was 747.5 minutes. So that means my x's will go from 0 to 747.5 minutes, and this bracket means x can equal 0, and this bracket means x can equal 747.5. So it's from 0 to 747.5, including those endpoints and everything in between. Now, in the middle school, you didn't use interval notation. You used a double inequality to say the same thing, and that looked like this. I'm going to write this up here. Does this look familiar? 0 is less than or equal to x, and x is less than or equal to 747.5. So this double inequality can be done with interval notation just like this. And as you go on into your advanced mathematics, you're going to use interval notation much more often than you're going to use inequalities. Now again, this is just an introduction, and we're going to work on picking up continuous versus discrete and our domain throughout this module. I hope you enjoyed that. Number 3. I'm more sophisticated than my little sister. Remember, she has that piggy bank. So I saved my money in a bank account that pays me 3% interest on the money in the account at the end of each month. If I take my money out before the end of the month, I don't earn any interest for the month. Wow. I started the account with $50 that I got for my birthday. All right. So I think we're going to start with a sequence. And we started the account with $50. So let me just start with a 50 right there. And then we will read the rest. Use a table, a graph, and an equation to create a mathematical model of the amount of money I will have in the account after M months. Now here again, they're asking us to use an M. You can if you want. I'm going to continue to use X's for my inputs here. All right, so now let's think about this a second. I am getting 3% interest. Now watch this carefully, okay? As soon as you see a percent, you've got to be thinking we're multiplying by a common ratio. And that common ratio will be, now you guys think 3% is 0.03, but I have a common ratio, my money's going to increase. So what I have to do for my common ratio is go 1.03. The 1 stands for 100% of the money that I already have in my account, and then I'm adding 0.03, which is adding 3% to that. So that's when my money's growing, I'm always going to have a common ratio with a 1 in front of this decimal. And then the percent it's growing by will be this part right there. So now we need some calculator help here. We're going to take this 50 and we're going to multiply it by 1.03, rounding our money to the nearest penny. So when I did that, I got $51.50. Now let's take our $51.50 and multiply that by 1.03. And I got $53.05. Now do this with the video. Let's multiply $53.05 by 1.03. Excuse me. And I now have $54.64. Remember, I'm rounding these to the nearest penny. And then if I take $54.64 and I multiply by my common ratio, 1.03, I get $56.28. So this is my first model, my sequence. Now, we need to think. 50, is that going to be the 0 term or the first term? So, when I had $50, so I'm starting with 50. So let's call that 0 months, month 0 right there. Okay, that will help me with my table and everything else I'm going to do now. And also I want to make one more point. If I take my money out before the end of the month, I don't earn any interest for the month. So I'm going to have values at the end of every month. Okay, if I take out my money before the end of the month, I lose that interest. So I'm not worried about things between these numbers, only these numbers, the amount of money I have at the end of the month. All right, let's do the rest of our models. So x equals, well, we said we were going to start with a 0. No diagram necessary. And I wonder if I can just go ahead and go by ones here. Keep it simple. 1, 2, 3, 4, and so on for every x right there. Now, f of x. Well, f of 0 is 50. F of 1 is 51.5, $51.50. F of 2 is $53.05. F of 3 is $54.64. And f of 5 is $56.28. And we're going to put our expression in when we get it, when we do this explicit formula. Now, let's try to fill out this stuff up here again. What do we have? A common difference or a common ratio? We are multiplying every time, and didn't we multiply by the common ratio 1.03? So let's tell the world that our common ratio is 1.03, and that answers these 3 questions right now. So if I have a common ratio, the sequence is geometric. The function is, well, a geometric sequence leads to an exponential function. So the data shows a pattern of exponential what? Now, I want you to think about this. Now the common ratio is a number bigger than 1. That means my money is growing, so I'm going to have exponential growth. Okay, let's scale our graph so we can plot the scatter plot. All right, so now probably went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's good. Now, look at the data. I'm beginning with $50. Does that mean I might want to break the y-axis? I think so. So I'm going to break the y-axis. And how about we start with a number at least, 50 or a little bit less. I probably started with a 50 right here. I did. Now, I've got to get up to $56.28. Let's see. Did I go 51, 52, 53, 54? I think I can. So let's see if I put a 51 right here. Yeah. 52, 53, 54, 55, 56, 57, and that's all I have room for. So now let's plot our points, and it's not linear, so we can't use a slope to do these very efficiently. So when you're doing something like these points right here, let's do this carefully. So when x is 0, f of 0 is 50. So let's go to 0 to 50 right there. And then at 1, f of 1 is $51.50. So 1, there's $51.50. That's going to be right there. Okay, f of 2 is $53.05. So there's 52, 53, and 5 cents is hardly going to show, but I'll try to go slightly over that. I'm exaggerating a little there. And then f of 3 is $54.64. So 3, let's go up to 52, 54, 54.50. I'm going to be slightly above that, about right there. Yeah, nice. Okay, and f of 4 is $56.28. Let's go up to 56. That would be $56.50. So $56.28 is going to be about right there. Nice. So see how I carefully did this? And remember what we said a moment ago? Okay, this is exponential. It's not linear. Now this almost looks linear. All right, but it's only because we have just a little bit of data right here. All right, let's hope this young man is investing this money for a long time, and if we continue to do this, we would slowly see the concavity. So when I put my line through the scatter plot, I'm going to try to show just a slight concavity that I can see already right now. And there it is. So do you see how I kind of showed the curve? It's curving a little bit more. It has just ever so slight concavity right now because it's exponential. It must have concavity. All right. Also something else. I did a dash line, didn't I? All right. And that is because if I take my money out before the end of the month, I don't earn any interest for the month. All right. So I'm not worried about the outputs between the points, only the points. This is an example of a discrete function. Okay, but we'll get to that in a moment. Let's go to our explicit exponential function, and that's f of x equals, and I look, oh, my first x is 0, so aren't I going to go a times b to the x power, a times b to the x power. Now, if you know what a and b are, you're good to go. So f of x equals a, my first output in the table, 50. B is my base, or my common ratio, 1.03 to the x. And there's my exponential function right there. Let's put that as an expression down here in our table. Beautiful. Now, our recursive formula. All right. Oh, let's put our function on our graph over here too. So, f of what equals what? Look at your first point. When x is 0, f of 0 is 50. So f of 0 is 50. And now my recursion equation, f of x equals f of, that's right, x minus 1. And what are we doing to the previous output every time? Well, we multiplied by the common ratio 1.03 times 1.03. And there's our models for this excuse me, this investment of money in the bank where we're getting 3% every month. All right, number 4. Now this problem, I'm going to introduce a lot of very advanced stuff at times. So remember, it's just an introduction. Okay, do your very best with it, and strive for understanding. Understand, we're just developing this understanding right now. So you won't pick up everything right away, and if you do, hats off to you. All right, watch this carefully. Take great notes. At the end of the summer, I decide to drain the 1,500-gallon swimming pool. So you know we always start with a sequence. And I'm going to start, the pool is full, so I'm going to start with 1,500 gallons. I notice that it drains faster when there is more water in the pool. That's because of water pressure. That was interesting to me, so I decided to measure the rate at which it drains. I found that 3% was draining out of the pool every minute. 3%. That's a common ratio. We're going to be multiplying by a decimal, so R equals. But now think about this. I'm draining by 3% every minute. Therefore, I'm going to be, how much water is going to remain in the pool every minute? Well, if I lose 3%, I still have 97%, which I'm going to write as a decimal, 0.97. So there's my common ratio. So now everybody take 1,500 times 0.97, and you will get 1,455. Take this number times 0.97, and you will get 1,411.4. Take this number times 0.97. Do you see our pattern of change is multiplication by 0.97? And what do you get? 1,369. Now take this number and multiply it by 0.97 to get 1,327.9. There's our first model of the sequence. Now, I want to know, are we going to call this the zero term or the first term? Well, the swimming pool was full with 1,500 gallons. So I'm considering that. That's when I'm starting. So I'm going to call that minute 0 right there. Now, a couple more things I want to think about. So how long will it take to empty the pool? All right, well, let's think about that. Let's get ahead. Let's go to our explicit formula right now. Let's see if you guys can do this. So, because this is a common ratio, my explicit formula is going to be the formula for an exponential function. F of x equals a times b, and because this is the zero term, I'm just going to go to the x power. Now let's fill in those blanks right now. So f of x equals a, that's my initial amount of water, 1,500 gallons. My base is my common ratio, 0.97 to the x. Now think about this. When will f of x equal 0? When will that pool be empty according to this model right here? Now, do you guys all agree that if I take 0.97 of any positive number, I'm going to have another positive number? So if we keep going and going and going, these numbers are going to get smaller and smaller, but they are never going to reach 0. Draining at this rate, the pool will never be completely empty. Now remember, this is an algebraic model, and some of you have done this before. Have you ever siphoned the water out of a kiddie pool? And yeah, it slowly drains, and when you get to the bottom, there's still a little bit of water in there that you usually have to let just dry out or wipe it out with a towel. I do this every year. My doggy pool outside on the deck. All right, so now let's put this to work. Okay, so our models now. All right, let's see. Let's go to a table. Yeah, no diagram, table. So this 1,500 we decided was our 0 term, and then the first term, the second term, the third term, the fourth term, and so on for every x value. And I think they wanted us to use m's for minutes, but you can use x whenever you want. Frankly, you can use any letter for a variable. All right? And I'm still trying to get you guys on this function notation, and you're comfortable with x and f of x. That's why I'm keeping this f of x and x. Now, when x is 0, f of 0 is 1,500. F of 1 is 1,455. F of 2 is 1,411.4. F of 3 is 1,369. F of 4 is 1,327.9, and so on. And we even have that explicit formula. I don't quite remember what it was. Let's just save that for a moment. I'm sure we could figure it out. Isn't it 1,500 times 0.97 to the x? Let's save that though. All right. So let's talk about what our common ratio is. And we remember we're draining 3% every minute, leaving 97% of the water. So I'm going to go a common ratio of 0.97, and that tells me so many things right here. The sequence is, well, if I have a common ratio, this sequence would have to be geometric. The function is, well, if I have a geometric sequence, when I create my function, it is going to have to be exponential rather than linear, which means the data shows a pattern of exponential, and because our common ratio, which is our base, is between 0 and 1, the water's draining. This is exponential decay. All right, let's set up our graph now. So, x is 0, 1, 2, 3, and 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you guys know we're going to be nowhere near 0 in this window. All right, now our outputs, our f of x's. Well, look at the data again. My smallest number up here is 1,327.9. Wow. I think I'm going to want to skip a whole bunch of numbers on my vertical axis, so I'm going to break the y-axis, just like that. And then start with a nice clean number between 1,327.9. So what did I do? Okay, I started at 1,200. And let's see, I think I'd probably go by maybe 50s. Let's see if this is 1,300. Oh, no, I'm going by 25s. 1,250. So then I have 1,275. Okay, hang on. 1,275, 1,300. 1,325, 1,350. 1,375, 1,400. 1,425, 1,500. 1,575, 1,600. Excuse me, I'm saying these wrong. Let's get this back. I'm sorry, I'm getting tired, you guys. Look, yeah, everything looks good right here. Now let's get to here. 1,525 and 1,550. Okay, there we go. No excuses, Mr. Gibbons. You have to be way more comfortable and more careful than this. Okay, so let's plot our points carefully. 0, 1,500. All the way up there. There it is. At 1, f of 1 is 1,455. 1,300, 1,400, 1,400. So just barely above that hash mark right there. Okay. At 2, we're at 1,411.4. Well, where's 1,400? I know you're here. There you are. 11.4. Well, that'd be 25, so 11.4, about right there. All right. At 3, we're at 1,369. 3. 1,300, 1,350, 1,375. So that's going to be right in there. Beautiful. And then at 4, I'm at 1,327.9. 4. Where's my 1,300? There it is. 25. Just barely above that hash mark right there. All right. And that's all the data I have right now. And again, this is not a lot of data. And that is why this exponential graph looks almost linear. There just aren't enough points there. But when I put my line through this, and by the way, is this going to be continuous or discrete? This is water draining. Water drains continuously, and that's why that's solid right there. And do you guys see the slight concavity I am trying to show? It's not perfectly straight. Okay, now let's go to our explicit formula, which we already did on the previous slide, but let's do it one more time. So exponential with a first x0, that's going to be f of x equals a times b to the x power. Or f of x equals, and a is your first output, f of 0 here, 1,500. B is your common ratio, which is 0.97 to the x. And now, let's put this down here. Okay, now our recursive formula. Oh, I always forget. I always put that right there too. So here's the recursive. F of what is what? Look at the first point. F of 0 is 1,500. And then f of x equals f of, always behind this wall, x minus 1 is, and this is the previous term right here, what are we doing every time? We're multiplying it by 0.97. So there that is. Now let's get to the real important stuff, our new stuff that we are introducing right here. So we already said that this is water draining from a pool, and water draining from a pool is continuous. That's why this is a solid line right here. So I'm going to say f is a continuous function with a domain of x equals. Now, wait till you see this. X can equal 0, but with this model, we would drain forever and ever and ever and never reach 0. So I'm going to have to go a bracket on the left and a parenthesis on the right. Bracket means x can equal 0, as we see right here. And this comma means I'm talking every number, every real number between 0 and what? And didn't we say earlier that with this model, the pool would actually never drain unless we did something else? So I'm going to say this is going to go 0, 2, and the symbol for going on and on forever is infinity. And infinity is not a number, so you can never reach it. And that's why this is a parenthesis. Now, this is the equivalent of this double inequality up here. Remember, bracket. I have an equal sign. X can equal 0. So 0 is less than or equal to x. And x is less than, that's why we have the parenthesis on the right, less than what? Infinity. We can never reach infinity, so we can never have an equals right there. Isn't that cool? Okay, we've got a couple more things to answer here. Okay, number 5. We're going to compare problems 1 and 3. What similarities do you see? What differences do you notice? Now, there's going to be a real easy way to make this comparison with simple pieces of the models that we have created for each of these problems. So, number 1 was the piggy bank problem. Remember? Now, little brother, I think, started with 5 pennies and then was getting 3 pennies every day. And then number 3 was the bank account problem, where we had $50 getting 3% interest every month. Now, let's just do a little chart like this. And I want to start, since they started us, well, we have explicit functions here and here. Let's talk about the general form of this explicit function. Now, isn't this f of x equals mx plus b, slope-intercept? So go down here and go f of x equals mx plus b. So I know my slope is 3 and my y-intercept is 5. So this slope-intercept works for what? A linear function. So the function is linear. And if the function is linear, that means if I created a sequence, it would be discrete with a common difference of my slope, 3. Which means there is no common ratio here. Does not exist. And then one more time, what's the slope in this problem? It's the same as the common difference, or this 3 right here. And what's the y-intercept? Well, it's the b, or the 5 right there. 5. And if you want to write that as an ordered pair, 0, 5, that would be great. let's put this into context then. Okay, so this individual started with how many pennies? Well, where do you see that? In the equation, the plus 5 pennies. And we see that with the y-intercept of 5 right there. So started with 5 pennies and added how many pennies every day? Well, we see that with the common difference or the slope. So 3 pennies every day. And now, was this discrete or continuous? Now, we're talking about the number of pennies in the piggy bank every day. And we can't have a fractional number of pennies, like 4.65 pennies. We're going to have like 5 pennies and then 8 pennies and then 11 pennies. That's discrete. Now, let's look at our bank account problem. And let's start with the general form of this function right here. And I hope you're recognizing this is exponential. F of x equals a times b to the x power. So a times b to the x power is exponential. F of x equals m times x plus b. That is linear. All right. So if I'm exponential, I do not have a common difference in my sequence. Does not exist. But I do have a common ratio. And what is the common ratio? The base, 1.03. All right. And then f of, well, where do we start here? That's an x, so I'm starting with a 0. And f of 0 equals, what did we start with? $50. And the base is, well, it's the same thing as my common ratio, 1.03, the base of the exponential. So let's put this one in context. So we started with how many dollars? $50. And gained what percent interest every month? Well, 1.03 means 100% plus 3% more. We're gaining 3% interest every month. And this, now remember this problem, usually when we have a common ratio, we honestly expect the function to be continuous. All right, but remember, if I withdraw my money before the end of the month, I don't get my interest. So we consider this one discrete as well. Very good. Now look at similarities and differences. Linear, exponential, common difference, common ratio. There's a linear function. There's an exponential function. All right. My pattern of change is a slope of 3. My pattern of change is this base of 1.03. I started with 5 here and 50 here. Look at the context, and they are both discrete. All right. Number 6, compare problems 1 and 2. And let's talk similarities and differences. So, problem 1 was the piggy bank problem. F of x equals 3x plus 5. Started with 5 pennies and received 3 more pennies every day. And then number 2 was the filling the pool problem. Okay, remember after we had 5 gallons in the pool, we decided we would add 2 gallons every minute. So we already have the chart filled out for the piggy bank. Let's jump to filling the pool and fill this up. Now this is f of x equals 2x plus 5 again. And isn't that mx plus b? That's slope-intercept. This is linear. And a linear function has a slope, which is the same thing as a common difference for the sequence. So the common difference is 2, meaning there is no common ratio. Okay. And then f of x equals, again, this is the same mx plus b, m times x plus b. And what was our slope one more time? That m is a 2. And what is the y-intercept? This b is a 5. And context. Okay, we started with how many gallons? We started with 5 gallons. You see it here. And what? The y-intercept of 5 right there. 5 gallons. And added how many gallons every minute? Well, it's our slope of 2, which is our common difference. 2 gallons every minute. Okay, good. Now, discrete or continuous. Now, the piggy bank was discrete because we're adding pennies 1 penny at a time. All right? But filling the pool, That water is flowing into the pool continuously, so that is continuous. And that's a great comparison and contrast of all the parts of these two problems. Last problem, compare problems 3 and 4. So problem 3 was our bank account problem. We started with $50, and every month we had 3% interest added to that. And then draining the pool. So we started with 1,500 gallons of water, and every minute we were draining 3%, leaving 97%. All right. We already have our chart filled out for the bank account, so let's fill out the chart for draining the pool. Now, isn't this f of x equals a times b to the x? That looks exponential to me. So these are both exponential, a times b to the x. And if I'm exponential, the common difference does not exist. What's the common ratio here? 0.97, meaning I have exponential decay. Over here, the common ratio was 1.03. That's exponential growth. And again, my general form, f of x equals a times b to the x power. Now, I need f of 0. F of 0 equals, well, over here, f of 0 was the 50. Over here, f of 0 is the 1,500 gallons. The base is 0.97. where over here the base was 1.03. Context. So we started with 1,500 gallons in the pool and drained what percent every minute? Well, if I have 97% left, I drained 3%. Now, look over here. We gained 3%. Over here we drained 3%. We gained because our common ratio or our base is bigger than 1. We drain because our common ratio is less than 1. That's how that works. And discrete or continuous. Okay, now, remember, the bank account we said was discrete because if I remove money before the end of the month, I don't get any interest. So we're talking about the money at the end of every month, not during the month. Now over here, this is water draining from a pool. And water flows continuously. Continuous. And that is 2.1. We took this above and beyond, but I have taken you with this video everywhere that this module is about to go. Now again, we're just developing right now, so don't be worried. I know some of this looks a little abstract, but this curriculum spirals, and we're going to see this stuff every day, and you guys will be experts. All right, thank you very much, and everybody have a great day.